Okay, here we have a tank of acid in a chemistry lab that is sitting 1.4 meters off the ground. And so it's here, and here's the ground. And so this is 1.4 meters. And the tank itself is 75 centimeters deep. So, we have this is 0.75 meters right here. And then there's some acid in there, right? So we have this acid in here, and there's the level, right? And then this little puka gets in it here at the bottom, and it squirts out, right? So it shoots out of here, and then it lands on the floor. Okay, so we get this little puka right here at the bottom, and let's say that it shoots out horizontally, and then it ends up landing on the floor. So we need to know, how far back do we need to stand, I guess, in order to not get hit by this acid. Okay, so we really need to look at how fast it's exiting. So if we say that it exits horizontally, then our vertical velocity, at the point it exits would be 0, right? We have some delta y right here. We know ay, right? Assuming projectile motion here, we know ay. We know delta y. We are assuming v naught y is 0. And so this gives us three things. What we could do is, going back to projectile motion, we could find the time from here. Actually, we can find the time, without needing anything with v naught x. And then again, with projectile motion with ax equal to 0, then we're going to have delta x is going to be equal to v naught x t. Okay, so we can find our time from the vertical characteristics here in the y direction, and then multiply this by the horizontal initial velocity, which is the horizontal velocity, which is constant here, right? Assuming projectile motion. When we go through the solving for the time, I guess we can go ahead and do this part here. We have, delta y equals v naught yt plus, 1/2 ay times time squared. If v naught y is 0, then this gives us time is equal to the square root of 2 delta y over ay, right? So delta y is going to be, if I pick my coordinate system, let's see, I haven't used blue yet. So this would be my coordinate system, positive y here, positive x there. And then we have delta y is negative 1.4. So this is negative 1.4. And then we have ay is negative 9.8, right? And so what we'll get for the time, we get 0.534 seconds. So the time here will be 0.534 seconds. So I'm just going to write that here. And just for the sake of having this picture next to us, I'm going to erase this so that we can have this figure here when calculating what v naught x is. So v naught x, this is something that we need to probably use one of our fluid dynamics equations for, which we've seen continuity equation, and we've seen the Bernoulli equation, right? Bernoulli equation can relate the height and the pressure and the speed, right? So we can get the speed from Bernoulli equation. The thing is, we need to pick a couple different points. There's a few ways that we can go about it here. I could let me just pick one point right on the inside. So this would be my, let's see, I'll use blue here. This would be 0.1 right on the inside, and this would be 0.2 right on the outside, okay? Then Bernoulli's equation can relate the pressures and the velocities here, and we won't have a height difference between them. I could have, if you wanted to, I could pick like 0.1 up here and take in consideration like a height difference. But we'll just do that. It works just as well to pick 0.1 right on the inside. So if we write out Bernoulli's equation, we have pressure 1 plus a rho g y1 plus 1/2 rho v1 squared is equal to pressure 2 plus rho g y2 plus 1/2 rho v2 squared, right? Okay. Now, if we say, y1 is equal to y2, right? So that's based on just where we chose the points. This is very much like, choosing a datum with our conservation of energy problems, right? Because this comes from that. So if y1 equals y2, these two terms will cancel, right? And we'll just have p1 plus 1/2 rho v1 squared equals p2 plus 1/2 rho v2 squared, right? So we can say here, well, let me go a little bit farther here first. Now, let's say that the area, because we don't know V1 or V2, right? But let's say that the area of 1, so this is, my area 1 would be across like this, and area 2 would just be, the size of this, the cross-sectional area of that little puka there, right? So if the area 1 is much, much bigger than area 2, right? So this is what we'd have. Then by continuity equation, since area, times velocity is a constant, well, area 1 times velocity 1 is equal to area 2 times velocity 2. If area 1 is really, really, really big compared to area 2, then velocity 1 is really, really, really small compared to velocity 2, right? So if area 1 is really big, then velocity 1 is really small, at least compared to velocity 2, which I think is in line with what we've seen. If you put a little hole in the bottom of a tank, and if you watch the water level, because V1, this would be, the velocity of the water in here. So it'd essentially be the water level going down here. If you look at the water level in the tank, how quickly it goes down, it's super slow, especially when you can compare it to how quickly it shoots out of here, right? So this is a pretty reasonable assumption to say, V1 is a lot smaller than V2. Kind of depends on the size of the hole, obviously. If the hole was like this big, then that's not going to work, right? But if it's just a little pinhole here and this is big, then this is pretty reasonable. We could go so far even to say that velocity 2. Oh, I'm so sorry. So I'm sorry, not velocity 2, but velocity 1. We could actually say that this is about equal to 0, right? This is essentially not moving in here, right? The water level in the tank is basically not moving, especially when you compare it to how quickly it's going out. So if we say that velocity 1 is pretty much 0, then obviously velocity 1 squared is 0 squared. It's even smaller, right? If velocity 1 were like 1/100th, then velocity 2 is like 1/10,000th. Very, very small. So Bernoulli's equation reduces down to pressure 1 is equal to pressure 2 plus 1/2 rho v2 squared, right? Well, how do pressure 1 and pressure 2 relate? If I have outside of it, this is atmospheric pressure. I have P naught. So, for all intents and purposes, this is just air out here, right? The increase in pressure due to air over 0.75 meters is really, really small. So P2 is basically P atmospheric, okay? And P1, this is going to be, well, I have atmospheric pressure here, plus however much the pressure increases with depth, which would be rho g y, right? Which is actually, that's the rho g y we got rid of a minute ago. So pressure 1 is equal to P naught plus rho g y. I could say rho g y1. And Oh, sorry, not P naught, but P atmospheric. Same as P2. So when I put this into Bernoulli's equation, I have, P atmospheric plus rho Gy, that's pressure 1, equals P atmospheric, that's pressure 2, plus 1/2 rho V2 squared, right? Of course, then these atmospheric pressures also cancel out. And what we have is, rho Gy is equal to, maybe I'll call that Y1, is equal to 1/2 rho V2 squared. There's a rho on both sides. This is just like mass canceling out way back in conservation of energy stuff. Density is just like mass per volume. Mass cancels out again. And we have, solving this, we have V2 is equal to the square root of 2GY1, which probably sounds really familiar to you. This is something we've been doing all semester long. When we had MGH equaled 1/2 mv squared, when we had the kinetic energy was driven by the potential energy, so all the potential became the kinetic, we got V was equal to the square root of 2GH. So with a couple little assumptions here, if this is small enough where we don't have to take into consideration the speed of this, and also basically saying that there's no pressure increase, atmospheric pressure is very small relative to the fluid, which is generally the case if we're dealing with air and then a liquid in the other, then we get basically the same thing, right? So the speed at x as a tank is just square root of 2GY1. So this gives us V naught x. So that was the V naught x we needed. And so we have here V naught x is the square root of 2 times 9.8 times Y1. That was just the depth of the fluid, right? 0.75 meters. So 0.75. And this means that delta x is equal to, V naught x times the time. Getting this, I guess, let me give you a number for this. This is 3.83 meters per second is V naught x, and then multiplying by that time we got, and it comes out to 2.05 meters that it shoots.